Our next speaker is Sandy Montague. Sandy's been involved in developing rhizobia and microbial inputs for farming systems for many, many years. He worked for Ciba Geigy a long time ago. He established his own business, sold it, started another one, and is one of the leading people in this particular field. Sandy.
Good morning, ladies and gentlemen. I would just like to talk about microbial products, inputs you use in your agricultural systems. And I'd like to thank Michael and Kate for a perfect introduction, because what I'm going to try and talk about is a very complex system in very simple terms. Our soils basically harbour our nutrients and our microbial communities that are really driving the whole system. And we have to think about a plant that is trying to grow in soil very similar to an animal, because it has microbial cultures on its surface and it has a microbial culture inside it, and they operate basically at the plant's direction. And it's just something that I'd like to explore and show you how we could probably change this around to our own benefit. Because today we've got very few cultures that we actually know how they operate, or microbial products that we know how they operate fully. We don't even understand all the cultures or all the microbial products that exist in the soil. We haven't yet identified them. So I'm just going to talk about the industry per se, and how hopefully we can actually do it better. Basically, if we look at what's available on the Australian market, you're all probably familiar with Legume Inoculant. We've heard Kate talk about subclover making nitrogen available for other plants. And that happens, but that subclover is doing it for itself. It's not doing it for the other plant. It actually, when it dies and those nodules senesce, release a high amount of nitrogen into the soil. The other interesting thing is Kate talking about that subclover being very good in high production systems. And the reason why it's good in a high production system is it has a high nitrate level. And basically we're converting that into protein. So if you just look at, we've only got 12 real products in Australia that we actually utilise. The major one would be Rhizobium. There's a little bit of VAM that's used in broadacre agriculture, mainly in vegetables. And all the rest are trying to convert other elements. So if we think about what we've got available, we've got nitrogen in the air, and any other element that we want has got to be in the soil. It might be insoluble, but it's got to be there. We've got to ship it in, because constantly we're shipping it out. If there's 12 there products that we've basically got available in Australia, and we look at what's overseas, this is just a list of what's available for disease control overseas. This is not the inoculants, just what's available for disease control. So consequently, we've got a long way to go at what's potentially available in Australia. If we look at basically our basic elements, major elements that we want is nitrogen, phosphorus, and all the other macro and micro elements. And nitrogen is the dominant player. So in a legume, such as lupins, 75% of that, or approximately 75% of all the nutrients taken up is nitrogen. In a wheat plant, it's something like 60-odd%. So we can see that we're really talking about nitrogen and phosphorus as our major elements, and we put on urea in big licks, and we put on superphosphate and MAP in big licks. Right? When we forget something, we have a problem. This is a wheat crop that's been sown across an old fence line, And basically, we can see the effect that nutrition has and good nutrition has, because basically we've harvested the nutrient in either paddock and not at the fence line. The global requirement for nitrogen comes out of the air. Whether we do it industrially or whether we do it by biological nitrogen fixation, and that requirement is somewhere between 150 and 200 million tonnes annually. And through the Haber-Bosch process, we make about 100 million tonnes globally. With biological nitrogen fixation, we're doing estimated somewhere between 50 and 70 million. And the interesting thing is that basically the more industrial nitrogen we put into the system, the less efficient our biological nitrogen fixation system is. And it's a basic feedback system for the plant. The plant will take its cheapest form of nitrogen. It costs the plant energy to actually run a biological nitrogen fixation system. So if you put on urea onto a legume plant, it will shut down its operation and basically take the free nitrogen from the urea. What are we talking about when we've got a Rhizobium and Legume Inoculant that we actually put on in the farm? We coat it onto a legume seed such as lupin or subclover, and we plant that seed. It is a very delicate organism, very easy to kill, and we normally have a lot of difficulty in actually delivering it. That's what it looks like basically when it's sitting on a end of a growing root tip. This is, in my career, the story about how a nodule forms has actually changed. So we must remember that what we currently think is gospel truth doesn't necessarily always apply, because I used to preach that Rhizobium will only form at the end of a growing root tip. And that implied that the Rhizobium actually got into the root of the plant. That's not entirely true. What actually happens is the root tip encapsulates the Rhizobium. And this is and just to show you the difference, we talk about a root, and the one there in the photo is about 2 mil wide, and the root hairs are very small. The nodules grow to quite large, right, and are easily visible. Right? But when we look at the process of what happens to form a nodule for nitrogen fixation, one of those root hairs actually grows around the Rhizobium. So it encapsulates that Rhizobium. This means that the plant's in control. And that feedback system is what's driving the whole process, or slowing it down when we over-fertilise. If we just take that further and we say, well, if we put on a heap of these Rhizobium bacteria and say we put a load into the system, we try and get as many nodules as we possibly can, what's the effect? And the effect is we can actually increase the nitrogen fixation in that plant. And this is work done by Rod Ruffley, New South Wales Department of Ag, and he basically doubled the yield from a lupin crop by increasing the numbers of Rhizobium as it germinated. And you can do this with other plants. It's not necessarily only with lupins. I have personally done this with a subclover, where we could increase the biomass of that plant by putting more Rhizobium into the system. They made more nodules and they fixed more nitrogen and they grew a bigger plant. Our problem in practicalities is that we have difficulty delivering. The higher the number of the Rhizobium around the seed it's sowing, the higher the nodule score. A big problem is we can't deliver them. When we actually operate in our farming system, we take a product, we coat it onto the seed, we plant the seed. That product is that delicate bacteria, and that delicate bacteria dies on drying out. So with a lupin crop, for example, we'll put 1.5 million rhizobium on each seed at application. We'll actually only deliver about or less than 1% as it comes out of the air seeder. And what kills them is actually the drying, not the air seeder, just the drying, and it doesn't matter how you do it, that's about what happens. But consequently, we have been trying to work out other ways to do this. Just looking at the Legume Inoculant, forming a nodule. That nodule contains leg hemoglobin. That leg hemoglobin is actually red, very similar compound to our blood. And if you cut open a actively nitrogen-fixing nodule, it will be red or pink. It won't be green or white. If it's green and white, it's actually a system not working. The different plants have different structures and they have different rhizobium that form nodules. So we currently produce 35 different strains of rhizobium and there's thousands of different strains. Those 35 strains are selected by mainly the New South Wales Department of Ag and CSIRO as the most productive strains for the crop. They do form different looking nodules. So when you look at a lupin crop or a subclover crop or a pea crop, they look significantly different. When we stuff up putting them on, basically it doesn't work. And we can see the yellow strip is the on the left-hand side. It's the plant without any nodules on the bottom. So it has a significant effect. Oops. Subclover in Western Australian soil, or should I say sand. And if you don't get the rhizobium, it doesn't work. And that actually is not correct. It was actually a rhizobium was put on there, but it was the wrong one. This came in just recently and just showing us how our untrained agronomists are having a problem with the delivery of rhizobium. Mung beans, liquid inject system, they put 1 vial of product that into 3,000 litres of water, which put about 500,000 bacteria per mil of water. Right? So you'd say there's plenty there. They then put 3 litres of blood and bone with that and planted the crop for about 40 hectares. Left it stand overnight, came back the next day and planted 300 acres with the same recipe that had been standing overnight. The end result was the farmers down the tube to the tune of $60,000 and the product that was left overnight has formed no nodules. Consequently, the liquid inject system is becoming very popular up north for delivery of rhizobium around seed because the bug is not drying out on the seed. And this is work done by Cole Douglas DPI in Queensland, and the WI stands for water injection system, the slurry stands for seed coated, slurry on seed. We are basically growing more nodules when we deliver it alive into the system at the point of sowing. There's a liquid inject system set up on an air seeder. Looks complex. They've got to run a line to each sowing tine, and it works. It's very easy to operate. Works well. Just a lot of lines involved. Also, one set up on a combine. Again, simple system, works well. There's a couple of other ways to do this, and one of them is to set up a system whereby you put the rhizobium liquid slurry straight in onto the seed in the air system, or in the air seeder system. This was two Queensland brothers that were looking at it and said, we can do this easier. And Cole Douglas did the trial work, and basically he said his airline system is not as good as water injection, but it's far better than peat slurry. And this is what it looked like. It was basically a box on the top of the air seeder, so that the spray was put onto the air seeder, into the box, mixed with the seed immediately before it went down the air seeder tube. It actually works quite well. Very simple system. That one worked at about 7.5 litres of water per hectare, which means that anyone that runs an air seeder could actually put this on quite easily. So just to sum up, legume plants control nodulation, which is a complex relationship, right? It costs the plant to actually run the nodulation process and to fix nitrogen from the air. The legume plant will delay nodulation of germination when N is in high concentrations in the soil. It will also shut down biological nitrogen fixation when N is applied to the soil during its growing period. But it will restart that biological nitrogen fixation when it uses up all the nitrogen in the soil. So we've got this feedback system that wants us to put on nitrogen, because the plant will actually grow better and you'll get more productivity out of it, just it costs the actual cost of the nitrogen. I'd just like to talk about one other operation that we currently help in Western Australia. This is Australian Mineral Fertilisers. You might, if anyone here have heard of them, they are Western Mineral Fertilisers. They've been very successful there. Currently selling about 10,000 tonne of organic type fertiliser, and it is low in nitrogen and phosphorus. They've built a big plant and taken the approach that we were poisoning our soils with MAP, and it is a processed fertiliser with some MAP in it and rock phosphate with all the other trace elements. And it's been an interesting journey to go along, because they have employed an independent consultancy firm called Living Soils Research to actually do a field trial every year with their product, and it's replicated, and they've got a lot of independent data. But I've just extracted a little bit out of the latest work, because I find it interesting of the effect that some of our chemicals are actually having on the survival of our biological systems and the growing of wheat, basically. So the AMF stands for Australian Mineral Fertilisers, and we've got and this is a replicated trial, and it was independently done, and the photo is representative of what the plant looked like in those plots. The MAP had Jockey on it. The fungicide 1 is Jockey, and I think fungicide 2 is Amistar. And you can see that some plants, or the MAP, has a lot less developed root system. That's fine in a normal year. It's when you have a drought and you're struggling for moisture that you'll get a yield reduction with that system, and the Australian Mineral Fertilisers comes over the top. The wheat yield, this is last year in a dry year, between MAP and AMF as Australian Mineral Fertiliser blend. And I'd just like to add that both of them are manufactured products. They actually cost about the same dollar input in weight, but the AMF has a lot less phosphate than what the MAP does, and the AMF program tries to, or endeavours to replace what you're taking out. So if you have a estimated 2 tonne yield, then it will put in 8 kilos of P, basically to replace what you're taking off the paddock. Whereas the MAP system is normally putting in that 15 to 18 kgs of P. Basically, we've got an in-furrow, no post-emergent fungicide and the yields. The in-furrow fungicide has retarded yield, whereas no in-furrow fungicide plus post-emergent fungicide has done better. So obviously they've got a result out of the fungicide. When we look at what's happened with the biological component of the soil, this is when it really stands out. The MAP plus an in-furrow fungicide, which happens to be jockey, is the least biota left in the soil, whereas the AMF with no fungicide is virtually double. Interestingly, when we put a post-emergent fungicide on, we have a reduction in biota left in the soil. One of the other measurements is the amount of mycorrhiza in the soil. So mycorrhiza are fungi that grow into the root system of the plant, back out of the root system and into the soil, and they transport water and nutrients back into the plant. And there's been a huge amount of work done, and there's more scientific papers written about mycorrhiza than any other single microorganism in agriculture. The interesting point is that mycorrhiza per se, or it is reported that mycorrhiza per se actually shut down their operation, or the plant shuts it down when they've got high levels of P concentration in the soil. So again, we've got this feedback system that when we use a fertiliser, we're actually shutting down a part of our biological process that is helping taking up that fertiliser. Just touch on the changes in the microbial industry. 10 years ago, the microbial input industry in agriculture were small, local companies, and we've been slowly bought up and gone out of our ways. Today, the large multinationals are moving into the area. So BASF purchased Becker Underwood last year. Novozyme purchased Natural Products last year. Monsanto put a microbial product on canola seed in Canada, released it last year, and Bayer purchased Anthrax in the USA 2009. Hopefully this means that we're going to get a lot more basic research. My problem with this system of the large multinationals moving into the area is that for them to develop a product, it has got to have a global market. It doesn't fit for them to develop a product for sale in Albury-Wodonga or on the Riverina Plains. And for that matter, even for a major problem in Australia, it still doesn't fit. An example of that is it's reported that Monsanto has a fix for the glyphosate resistance in plants, and that technology is based on a DNA fix. The research and development to do that is very substantial, but however, Australia's major problem at the moment in the cropping industry would be ryegrass resistance to glyphosate. That market in Australia is not big enough for Monsanto to make the investment today. Consequently, when we think about these companies producing answers for some of our microbial problems in the future, it might be difficult to get them to do the work. What we do, basically we're a fermentation operation. We produce freeze-dried Rhizobium. That's a process we developed, and currently we're the only producer globally of a freeze-dried, commercial producer of freeze-dried Rhizobium. We also produce a peat culture, an Azotobacter, an Azospirillum and a Bacillus culture, and make some cultures for bioremediation in hydrocarbons. Basically, fairly simple process in stainless steel pressure vessels, normally aerated and spun down and freeze-dried. We get a lot of help from the Department of Agriculture, Sydney University and a number of other places. This is the area of research for the future that I believe is going to come along and dominate in the future. We know very little about it today, and hopefully we'll know a lot more about it in the near future when we get some serious players actually looking at the mechanisms that are going on. Thank you.
Could you comment on the soil in Western Australia? Does it have high levels of total phosphorus? Do the soils in Western Australia, the sandy soils, have high levels of total phosphorus in their makeup? Around here, I'm starting to notice that we have very high levels of total phosphorus, but fairly low levels of available phosphorus. So could you just comment on that? And just about the sands in Western Australia, whether they're in the same boat or not.
Australian farmers have been putting superphosphate and phosphate products on agricultural land for a long period of time, and that has built up a pool of insoluble phosphate in the soil. And that phosphate is cycling, and it will come out of that pool with microbial activity. The problem is we don't really understand what the major drivers are. There is work being conducted overseas to try and understand the mechanisms. We look at it and think about balancing up all the other nutrition and reduce our actual amount of phosphate going into the amount that we're actually going to take off annually. So if we're going to take 5 kilos, we'll only put 5 kilos in. When we put 5 kilos in, some of that is bound almost immediately. Consequently, we have to get some back out to maintain productivity. And in the main, that's been happening. And I think it's a mixture mainly of good nutrition. And by good nutrition, I mean all the other elements required. And having good organic carbon, having good biological processes going on as a holistic system. I'm a great believer in natural products such as kelp, humate, fulvic acid. We think about it, our waste systems run to the sea. We should be taking a lot more products out of the sea and bringing them back into our agricultural system. And I don't care what they are. I'm just saying, as a fertiliser system, we should be going to the sea and bringing back products out of the sea. Today, there is no simple answer to how to cycle insoluble phosphate. Mycorrhiza do it. We haven't got an economic mycorrhiza in the Australian broadacre system today. There will be one in the near future. However, that's going to have to be with good nutrition. It's not going to work just as a single silver bullet.